session and the day. Xiaohan will be talking about angular momenta in disk galaxies.
Okay, can you hear me? Okay, thanks for the introduction, and finally we come to the last talk of today's session. So I'm glad to be here, and my name is Xiaohan Wang, and I'm a PhD student from Xiaohan University. And I'm here to introduce some of my recent works about the properties of manga star-forming disk galaxy with different studies. Yeah, I've changed my topic slightly. Okay, so I believe I don't need to take much effort to convince you about how diverse and complex the galaxy is. So since people have started learning about galaxies, they soon realize that galaxies are very diverse in properties. So we know there are Hubble type diversity in morphologies, and we know there are star-forming galaxies, quiescent and Green Valley galaxies. But if we focus on the subcatalog here, which is the star-forming disk galaxies, which seems to be more homogeneous in the star formation and morphology, we still know there is much diversity in this subcatalog of galaxies. So this inhomogeneity can be seen from a basic diagram here, which is the galaxy size versus stellar mass, and this is very basic properties. This is a very basic parameter of galaxy properties. So we already know here that on this parameter space, we can see a large scatter of star-forming disk galaxies at a fixed stellar mass. So the question is, why do galaxies at fixed stellar mass have different sizes? And are we able to make some interpretations from that, from the observation results? So lots of people have made a lot of work about the correlations between galaxy size and galaxy other properties, and people have made a lot of effort to interpret possible evolutionary tracks on this. And this is a theoretical view of this can be seen and summarized in this figure, which is from Capillary 2016, and you can see the galaxy morphology and also the age mass-to-large ratio of the property is changing along galaxy size at a fixed mass for these galaxies. So with the progress of observations, and this is the motivation of this work, to further give a better and more complete description of galaxy properties distributed on the size-to-mass plan for these star-forming disk galaxies with the MaNGA galaxy samples. So let me first show some basic view of how these properties distributed on this size-to-mass plan. So this is our sample of MaNGA star-forming disk galaxies, and the x-axis is stellar mass, with the y-axis is effects readers. So the color here are the structural parameters, and the left-hand side is the relative central density, and on the right-hand side is the surface index. So redder colors mean that the galaxies are more concentrated with more dense and more Devenculus-like mass profiles. So a basic view here you can see is, well, the galaxy with smaller size fixed mass, they tend to have more concentrated mass profiles and more denser cores. This is also confirmed by the galaxy kinematics, where we calculated the rotational parameter, which is lambda here, and this is normalized parameter, which indicates the rotational support with galaxies. So higher values, where the blue point here means the galaxy is more rotation dominated, and this definition of lambda here. So you can see, well, the galaxies with larger size fixed mass, they also tend to be more blue, so it is also consistent with previous results. That's the galaxies with larger radii fixed mass, the more disky, not only from the structural properties, also from the kinematic results here. And another thing we care about is the specific star formation rate and the star formation history of these galaxies. So here I show the distribution of specific star formation rate of core galaxy on size versus mass plan. An interesting thing here is you can see, well, it seems that it is kind of a mass of distribution on this on this size-to-mass plan, that we cannot see much dependence on galaxy size of specific star formation rate. So it seems that, well, galaxies fixed mass with different radii, they seem to have a similar specific star formation rate at this short time scale. And what is more clear here is the mass trend that galaxies are decreasing their specific star formation rate with increasing mass. So this is why it's a little bit strange. Why do galaxies with different size share similar specific star formation rates? Okay, but the advantage of MaNGA galaxies is we have the spatially resolved maps of the stellar population properties. So we can calculate about the, so we can investigate about the spatially resolved properties of stellar population and specific star formation rates. So what we are doing here is we calculate the difference between central and global specific star formation rate and also the age indicator, which is the D4000 here. So okay, so the left-hand side is the difference between central and global specific star formation rate. The right-hand side is difference for D4000. So the color bars inverted to be more consistent. So the blue colors mean there's more specific star formation rate in the center, which means the galaxies have blue centers. So it is clear, you can see here that the galaxies with smaller radii at fixed mass, you can see more blue points here, not only for the specific star formation rate, but also for D4000. So these two indicators show consistent results. That galaxies with smaller radii at fixed mass, they tend to have blue centers, but galaxies with larger radii tend to have red centers. And I think it's also shown in previous talks by Aldo, that galaxies with smaller radii tend to have blue centers, even though they share similar specific star formation, global specific star formation rate. So here, I come to a quick summary of what I just said about the properties of galaxies with different radii. So it seems that, well, and this is the previous color I just shown, that is colored by galaxy with no support. So galaxies with larger radii fixed mass, it seems to be more disky, not only in kinematics, but also in structures, and also show red centers instead of blue centers. And the galaxies with smaller radii, they tend to have blue centers. And here I show some images of the example of the galaxies. So galaxies on the top, you can see here they tend to be, you can see the beautiful extended structure of disks, and you can see the beautiful spiral arms, and they are more extended than galaxies on bottom. The galaxies on the bottom images, these are the example images of galaxies with smaller radii. And you can see, okay, they seem to be more smooth, more clump, and you can also see the color difference between the central and outer regions. It also turns to be more smooth in the bottom region, which is also consistent with what I showed before, that galaxies with smaller radii, they tend to have bluer centers. Okay, so the question is, why do we see that? So why do we see a galaxy with large radii turn to be more disky and also the red center? Okay, so what I've just said before seems to be consistent, because there are some theories like galaxies with higher momentum and more disky structures, which and this would pretend the gas to move into the center to feed the central star formation. So they're consistent with the stellar population gradient here. But what I want to investigate is the total mass distribution within VFX readers. So what we are doing here is we are our group is modeling, is doing the gem fitting for all the MaNGA galaxies. So gem is the genes anisotropy methods, which is the 2D kinematic modeling, and it contains the model of stellar components, also dark matter components. So from this gem model fitting, we're able to derive the distribution of not only star components, but also dark matter components. So from this result, we can further constrain the distribution of dark matter to further understand, is there any difference of dark matter for galaxies with different sizes? Okay, so here is one example of the gem fitting, and you can see the top line is the maps of the VR mass, which is v squared plus dispersion squared, and the bottom line is the map of the velocities. You can see the observation results here, and this is the model results, and this seems to be quite consistent. So the fitting, so the fitting is good enough here. Okay, so from the gem fitting, we can guess the total mass distribution and the total mass within VFX readers. And from these, we are able to calculate the dark matter refraction within VFX readers. So I'm coloring this size to mass plan by the dark matter fraction from VFX readers. The total mass, I will see dynamical mass is from gem fitting, and the gas mass is from Koenig-Smith law, and the stellar mass is from PBXF fitting for the MaNGA spatial resolved maps. So you're able to calculate the mass of each pixel and calculate stellar mass within VFX readers. And here is the result of the dark matter fraction distributed on this plan. So you can see here it is clear that the bluer points means they have higher dark matter fraction. So it seems that the larger galaxies, they also have more dark matter within VFX readers, while the smaller galaxies have a smaller dark matter fraction. So it is also consistent with the previous results. That is, the more dark matter fraction is band for readers means that the galaxy is more stable because there are more dark matter to stabilize the galaxy system and make it more stable to support and keep these structures. And also a possible reason that's why these galaxies also have higher momentum and also prevent the central star formation to produce the red centers we see in previous observations. Okay, so it seems good and everything is consistent, but I want to read the question here is, do these galaxies with different radii have different dark matter profiles? So the question is, if we simply assume that all galaxies fixed mass, they share the same dark matter profile, like the NFW and it is independent of size, well, the galaxy with large radii and it will also seem to lead to this relation because galaxy with large radii will simply cover more parts of dark matter and also leads to higher dark matter fraction. So the question is this simply from that, or it is possible that galaxies with large radii could also have more dense dark matter distribution in the center? Okay, so I'm going to show something that is preliminary, and we are still working on that. So let me first cite some results that is for higher redshift galaxies. So it is a work from Genzo 2020, who made the kinematic modeling of some V equals 1 to 2 galaxies. And they also calculate and see similar relation that galaxies with larger radii have higher dark matter fraction, and also fits the slope of the dark matter profiles. So here there's a parameter to parameterize the concentration of the dark matter profile. So the alpha equals 1 means the NFW, and higher alpha values means the distribution of dark matter is more cusp. So what they see is the galaxy with high dark matter fraction also have more cusp distribution of dark matter. So is this also true for the local galaxies, for the MaNGA galaxies? Okay, so the thing here is we simply adopt the empirical relation of NFW profile, and that is depend on stellar mass only. So we use the empirical model that is from Motor 2013 and also Justin and Matthew 2014 work, which the halo property is the only dependence on mass and its independence on size. So we can see here is this is the derived dark matter fraction based on that, and you can see also the beautiful color pattern that the galaxy with large radii have larger dark matter fraction also, and it's also expected. And I think this is quite similar with what we have seen before. So at least now I'm not sure whether this is consistent and whether this simple model, which is independent of size, can simply produce what we just seen before, that galaxies with larger radii have higher dark matter fraction. So I still put a question mark here. But a simple thing I want to say here is I want to make a quick investigation with central dispersion. So I'm coloring these two figures with the delta dispersion, because here if we assume that all stellar matter enough to support the stellar dispersion, we don't need any dark matter more to support this central dispersion. So I'm coloring this by this delta dispersion, and the left and difference between left and 2 are two different PBXF fitting ways to get the stellar mass map. Okay, so the higher values, which is the redder points, means the dispersion is higher than expected from stellar components. So we will need more dark matter in the center to support this kinematic. Okay, so it seems that we can see some signatures here that there is a slight difference between top and bottom. There seems to be more red points on the top, which is also consistent with previous results, that these galaxies have more cusp dark matter distribution in the center. But I would say this is also preliminary because because the detailed investigation of stellar mass needs very careful calibration of the stellar probabilities and this kind of thing. So I will just leave this question open and see we are still working. Okay, so yeah, this is what I just said. We are still working on this, and we are trying to make some combination of stellar probabilities and that modeling to further constrain the dark matter distribution of these galaxies. Okay, and this is my summary, and all questions and comments are welcome. Thank you.
All right, any questions before we move on to discussion session? We have time for one quick question. Okay, yeah.
Great talk. I have a short comment that we should be careful when interpreting the dark matter fraction within RE, because naturally with a higher RE, you enclose a larger fraction of the dark matter halo into it. So naturally, you would expect a higher dark matter fraction for given stellar to halo mass relation. So careful with that.
Yeah, that is.
I think a better way is to directly compare the RE and the enclosed dark matter mass. Then that can be compared with different dark matter profiles. That will be a more direct comparison with for that.
Okay, thank you. Yeah, and this is the point I'm trying to make, that you are trying to see whether it's simple or trivial that you just as the larger galaxies become more enclosed. So what I just say here, okay, it seems to be a signal that galaxies are really also have more dispersion, so which means they need more matter to support the kinematics. I agree that we need to be very careful when calculating the mass also because of this one. So this is something anyway, and we'll still working that. And thank you for the comments.
Okay, let's go ahead and thank all the speakers from today.